So hopefully you're plenty familiar with the way lists work at this point. If you're not, make sure you finish lab 2 first before you moving on to this one. So whereas you've been learning about, why does this thing not work anymore? That is annoyingly disappointing. All right, so whereas a list was just simply, your array list was just simply a array that you would manually transfer items into a new array from, basically just it was arranged so you could view it as a contiguous block of memory that you that just simply handled resizing on the back end, and you didn't need to really concern yourself about it too much unless you had to reallocate. A linked list is substantially different. Okay. A linked list, so if an array list again is just simply one contiguous block of memory, a linked list is basically the complete opposite of that. A linked list is comprised of what we call nodes, which are boxes that basically hold the data. A node basically, that's what we call node class. So a node doesn't really look like much. But basically has two variables in it, and that's really all it has. It has the pointer to the item that the node contains, right? So it has the item being stored. This is analogous to basically how an array list holds, each slot in the array list holds an item, right? But the other point that it has is, at minimum, it has next, which is a pointer to the next node in the array list, which is somewhere else in memory. So this one points to this one points to this one, and this one points maybe to some other node, and so on and so forth. So these nodes are basically scattered throughout memory, God knows where. The way I like to view it is it's a scavenger hunt, right? Each node each item in a scavenger hunt, or each location in a scavenger hunt, contains the pointer, the reference, the instructions on how to get to the next item. So at first, for a lot of students, it looks very and so that's important that I kind of explain it, that it's pointing to the next item before I pull up the code, because the code, at least when I looked at it the first time, when I was learning linked lists for the first time, looks weird. This is the same code that you'll be using for both for basically both for either assignment you choose, both the Josephus problem and the I'm having trouble wording today. Both the Josephus problem and the solitaire encryption problem. So you'll be using this file regardless. So I'm just going to do a quick walkthrough of it. Okay. Come on. Over here. Okay. Circular linked list.java. Yes, come on. There we go. Excellent. All right, circular linked list.class. Here we go. So let's go ahead and look through it. So first off, it's a circular linked list. You aren't going to be using linked lists, the linked list built into Java. You're going to be using, you aren't going to do that until we're well past this module. You're going to be using the one we build here. This is a circular linked list. You'll learn what it means in a bit. You can erase that package if you don't contain it in a package. That's fine. Public class circular linked list, it holds generics, and it implements iterable E. That means that it implements the iterable interface, which means that you can use the for each loop on it, which is useful for the Josephus problem, or not using the for each loop is actually the for each loop itself is not useful, but the fact that you can iterate through it is useful. Less useful for the solitaire encryption, but I'll get into that. Your variables, head and tail. You keep track of the beginning item in the list and the last item in the list. Rather than having, an array, you just keep track of the first item, your starting point. And we also keep track of the last item because that makes our job a heck of a lot easier. So nothing exciting over here in terms of your constructors. You got to fill all those out. I've already created a toString method for you. The toString method is designed to crash if you don't do it, if your circular linked list isn't implemented correctly. The crashing is a feature, not a bug. So if it crashes, that means there's something wrong in your methods. Okay, I'll go over this in a bit, probably in more detail on Wednesday, the iterator. But simply put, that is what will make your job, if you're doing the Joseph's problem, a lot easier. And it hooks into the method you write. Okay, here's the first thing that is implemented for you that is notable for you. This is the node class. So first off, this is basically our first use case, our first real use case of a private class inside of another object, right? So we have a class inside of a class. It's a private class, meaning that you can't create nodes outside of this class. You can only create nodes inside here, okay? Meaning that if you're outside of this class, you can't manipulate nodes. That's good. You don't want people to manipulate the innards of the class, just like you don't want people to manipulate the array directly in an array list. Static means that the nodes can exist without necessarily being inside of a list itself, right? And that's useful because what we do is we create the node and then we put it into the list, okay? Okay, and then it's got a constructor, which we'll get into, and then we've got two items. item, so it holds some item of some type. This will most likely be an integer. And then node e next. So this is the weird part or the weird thing for me when I first read it. It was node e and then node e here. How could it, be referencing itself like that? But it's not one of those Matryoshka doll situations, as I say in the videos. This is, again, saying this is a memory location that stores in it. This is a variable that stores in it the memory location of the next item. Your first task for this homework is to complete the add method. You'll want to complete the add method because you need to be able to add stuff to this. I would switch that false to a true. And that's all you have to do for this add method. There are 5 cases for doing add. Okay, given an index and an item, you want to add this node to this. There's 5 cases, 5 basically conditions that you check. The first is checking if the index is valid, right? Can't add it to a negative index, and you can't add it to something that is out of bounds on the right side. So can't add it to something that's greater than the size. You can add to the index size to add to the end of the list. In fact, you need to be able to do that. Then you have these cases that you want to check in order. The reason I put this here is because doing these in order avoids a lot of nested if statements that you would otherwise have to do. By checking it like this, you only need your if statements is just a single if else block. You've got this if statement and then the rest are an if else block and it doesn't have to be deep. It doesn't get, if without this, it would be these things would get nested very deeply and it gets ugly. So first thing you want to do is check to see if your list is empty. Because if it's empty, then you got to do a few things to make sure that the head and tail get set correctly. The next thing is adding to the front of the list, because you got to update what the head is, the first thing in the list. If you're adding to the end, you got to update what the tail is. So that requires a condition. And anywhere else, that's very straightforward. That is going to be the same algorithm that we see in all the videos. Okay, so that one's fairly easy. Now, in my linked list lecture videos, for the singly linked lists, okay, now this is a singly linked list just to make it easier. For the singly linked lists, I only had 3 conditions. For the doubly linked lists, you had all 5 of these conditions. I did all 5 of these. The difference here is that this is a singly linked list, a circular singly linked list. So you need to follow all 5 of the conditions. Why? Because you're also keeping track of the tail. If we weren't keeping track of the tail, we'd only need, I think, the 3 conditions. All right. But again, if you haven't watched this, just watch the videos, because that will be extremely useful to you. If you are doing the Joseph's problem, everything that you need is in this class, and the problem can be solved in the main method. Okay? The problem can be solved in the main method if you're just doing the Josephus. And what do I mean by that? In case you did not get the memo or missed the memo or missed me announcing it in class, if you go under modules, we have, under module 4 assignments, it has 2, not 1, but 2. You don't have to do both. You're just doing 1. Josephus problem is the easier one, and the solitary encryption, I would say, is twice as much work, but it's worth 20 extra points, which is a substantial amount of extra credit points. Okay? And they both use that same base code, right? They both use the circular linked list.java, but it's got a separate class to do the encryption. It's also got a deck of cards. By the way, I would highly recommend, if you don't, for working with linked lists and learning linked lists, do one of two things. Either draw the code you are doing, okay? You know, draw the step-by-step process of how these linked lists work, right? Because that's what I do on the videos, okay? So I would draw, okay, we're adding this node, which connects over here, which means that we need to, that once that's connected, we move that pointer over to reference that. So that's and that's going to help you understand it. If the drawing doesn't work, I'd recommend getting something like a deck of cards and then some like pencils or something to represent the pointers and just laying them out and like use the pointer, use the pencil to like connect the items, and then you can physically move things around and kind of follow what your code is doing. Using a physical representation will really help there, especially for the solitaire encryption problem. Okay. The other reason but a more practical reason and more immediate reason as to why you might want to do this is because the number of questions on the exam will ask you to draw the operations for like adding or removing in a linked list. Speaking of an exam, not next week. This is week 4, not next week. That's week 5, but week 6 in lab will be your exam. So that means that it will be the 23rd. So plenty of time, right? What will it cover? Through linked lists. Nothing about stacks, nothing about queues, even though they'll be introduced beforehand. You don't need to cover it. It goes up through linked lists. Why? Because that is what we consider important. This is, like I said, the first hurdle. Okay? And if you can get through this, you can get through the rest of the class. Okay? Okay. Last thing before I move on. For those of you who are doing the solitaire encryption problem, please just pay attention right here. For those of you who are doing the solitaire encryption problem, for actually doing the manipulations for the solitaire encryption, actually do get yourself a deck of cards. And for all the operations that you are doing for that solitaire encryption assignment, think about how you would do these operations with this deck of cards, and you've got only one hand, but you've got unlimited table space, okay? Because that will help you simulate the restrictions that you have on the computer. Now, the solitaire encryption puzzle does really help you kind of understand, oh, so this is what linked lists are good at, which is being split apart into multiple lists. Because with linked lists, it's trivial to do things like this that are really difficult and time-consuming for an array list. You just split it up. You just move everything. You just slowly move every item that you need to into a new list, one at a time. Each of these is a constant time operation. And then so it takes n over 2 time to basically split it up. And then it can take either constant time or n over 2 time to put them back together. But basically manipulating it like this will help. The other thing is that if you're doing the solitaire encryption, there is not a get and set method in the circular linked list class, but you'll want to write one, a get and set method if you're doing solitaire encryption. If you're not doing solitaire encryption, don't worry about it. if you feel like you can do solitaire encryption, but you're worried that you might not be able to, start out with solitaire encryption. Worst case scenario, you've still written everything you need to do the Josephus problem. Okay. All right. So okay, that is it. What I'm going to do is yes.
Would we be able to if we do the Josephus problem, and then later this semester we try to do the solitaire encryption, could we still get some sort of extra credit for doing it?
I'll think about it. Okay, I will think about it. I would probably have to, prorate that extra credit, based on okay, it was extra. You did the extra credit, but it's much later than it was on the due date. So, but I will probably give some amount of extra credit for doing that. Because if you're going to go through the effort, I might as well respect that. Okay. So I'm going to go start on this end today. On Wednesday, what I'll do is that we will hold this over Zoom. Okay. Man, that HDMI cable is hard to pull out. Stop recording.